Good morning, everybody. It's foggy. I love the fog. We first moved to Fresno back in 2001. It was foggy like this all the time in the wintertime. It's been like hardly foggy in the last 15 years. So it's kind of nice to see it. It means that there's actual moisture somewhere. All right. I am not a doctor, but I play one on TV. No, I actually dropped out of anatomy and physiology because they had made me memorize too many things. But we do need to talk a little bit about the biology of the eye, its structure, and all that kind of stuff, so we can start talking about how these built-in lenses, right, are used so that we can see stuff, but then also be able to talk about when there's issues with the optical system and how do we go about correcting visual issues for people that can't see clearly for a variety of reasons, right? So main features, right, of the optical system from the point of view of a physicist, okay, is actually not the lens. Everybody focuses on that lens, right? But that's not where most of the refracting power of the eyeball comes from. Our eyes use refraction because you have light that's traveling in air, and then it enters the eye and travels in fluid, which I don't understand what's so funny about this fluid, but it is called the aqueous humor. The thing that refracts most of the light in the eyeball is the cornea. Okay, and that cornea, right, is that outer surface of the eyeball, right? And so when you go about correcting vision without glasses and without contact lenses, like you're actually going to permanently correct the eye, typically it's not the lens that you are working with. It's the cornea. I used to wear glasses, but about 10 years ago, I got laser eyes. That's what I like to call them, right? My eyes had finally stopped changing every year. If you wear glasses, your eyes can slowly change or quickly change depending on problems with your eyes. I was severely nearsighted, but I finally got into my 40s and the doctors gave me the A-OK to get LASIK. And so that procedure didn't do anything to the lenses in my eye, but did everything to the cornea. It reshaped the cornea because it's the cornea that gives most of the refracting power of the eyeball. So if the lens isn't like the main player, then what is the lens responsible for? So the cornea does most of the bending of the light to try to get everything that's out there into focus, an in-focus image on your retina, right? Now the retina, okay, consisting of the rod and cone cells, I can never remember which one does which. It's the rods that do the black and white, isn't it? Pretty sure, okay? And then the cone cells are responsible for the color, the RGB. There's like three different frequency responses in the cone cells. In the cone cells. So we have a lot more rods in the fovea, right? That area where we've got this concentration of light collectors. We have a lot more rods there. And so the human eye is actually fairly sensitive in like the black and white portion of our vision, meaning that like at night, different people have different levels of like night vision. But generally, colors will kind of go away. If you've ever been outside, like walking, and all the light you have comes from the moon, right? Moonlight. It's kind of hard nowadays because we have so many light sources everywhere. But generally, what we lose is all like color information. Like a red shirt won't look red, right? If it's too dark, that kind of stuff. But we'll be able to see the contrast, right? We'll be able to see the differences in the black and white pretty well. While we're on the subject of night vision, do realize that it does take time for your eyes to adjust to different levels of light. And it has very little to do with actually how big your pupils are. That helps, of course, right? Our constriction and dilation of the pupil helps us not only with our fields of view, but also with the amount of light we're letting in and not getting headaches. But there's a chemical called rhodopsin that needs to build up in the cones. And rhodopsin can take like half hour, 45 minutes to get up to its full level. Rhodopsin can get driven out or destroyed just by having the lights turn on. If you've been sitting in a dark place or something like that, and all of a sudden a bright light comes in, like a car drives down the road or something, your night vision can go away like that. And then it's another half hour before you'll get the full capability back. So the trick for not destroying one's night vision, if you see a bright light coming and you've been adjusted to it, is to close one eye or to cover one eye, okay? So that you can see, right, what's going on with the bright light, but then when you want to be able to see in the dark, one of your eyes won't have all the rhodopsin destroyed in it. This is, by the way, why pirates wore patches on their eyes. It wasn't because they were missing an eye, okay? It's because when you go down below decks, it's totally dark. And if you're coming from the bright sunlight to below decks, you can't see anything. You're effectively blind for a few minutes, right? Well, if you had one eye with a patch over it and you're outside in the sunlight, this eye is getting used to the dark, right? You go down below decks, you flip your patch up, you can see, and then before you go back up, you put the patch back on, and you can go. So it was an instantaneous change, being able to switch between dark and light vision. All right. That was a slight tangent, but a fun one anyway. So what does the lens do? If the cornea is doing most of the work, what's the job of the lens? The lens allows for fine adjustments to our optical system. And by fine adjustments, I want to demonstrate this by you doing an experiment, okay? So what I want you to do is I want you to hold your hand out. You just want to be able to see your fingers. And I need you to hold it out so that you can see as far across the room as possible, right? So some of you might need to turn around to look at a far corner or something, but you really want to have a pretty far distance, okay? And if you hold your hand out in front of your face and you switch back and forth between concentrating on your fingers up close and then concentrating on what's far away. If you look far away, you'll notice, if you don't look at your fingers, that they are slightly out of focus, right? That your eyes are focusing on something very far away. And then as you switch that vision to the up-close fingers, you'll notice the background goes blurry. I want you to look at your fingers, then look at far away, look at your fingers, look at far away. Switch that back and forth fairly rapidly. Don't spend more than 1 or 2 seconds on each one. And concentrate on the feeling that you get in your eye as you do it. Can you feel something going on in your eye as you switch between far away and up close? What you're feeling are the muscles in your eyes accommodating for the difference in object distance. Got really big object distance, up close object distance. The lens will get pulled and squished by the muscles in your eyes so that you can focus on far away and up close. The lens is an accommodation mechanism. We call this feature accommodation of the eye, where we can focus up on something really close versus being able to focus on something far away. Usually we're not paying attention to what our eyes are doing. And we will think that everything that we're looking at is at equal focus, right? High nosebleed section there in the back, right? Some of you are looking at your computers and all that kind of stuff, obviously doing physics, right? But you'll look at the thing in your screen, right? And then you'll look up here, and you won't think about how, oh, my screen's out of focus now, but I can see the board, and then, oh, the board's out of focus, I'm looking at my screen. What our brain does is it integrates all of that information and makes us think that everything's in focus all the time, when in fact it isn't, okay? In fact, in our vision, there are blind spots. There's portions of our vision where we can't see something because our optic nerve is getting in the way, but our brain kind of fills in the gap. It does it with a lot of different tricks, including but not limited to our eyeballs are in constant motion. So even though I'm like staring at you, right? My eyes are actually like darting around and trying to get all of the visual field that then the ocular vision parts of my brain puts together as this reality that I'm experiencing, right? And so even though not everything's in focus all the time, my brain is remembering when it was in focus just a few milliseconds ago, right? And giving me this visual picture. It's kind of hard for us to, like, we really have to sit and concentrate and go, I'm looking at my fingers and I can kind of tell that everything back here is out of focus. The lens will change its shape and change its focal length in order to help keep distant things in focus versus up close things in focus. And we'll do the math of all of that. And we'll learn how even little tiny changes in the ability for our eyes to accommodate can lead to vision problems, like the inability to see far away, be able to focus on things that are far away, or the inability to be able to focus on things that are up close. All right, so we did all that, all right? So, so a lot of the pictures I'm about to show you are from various textbooks, including your own. And I need to just acknowledge here, because I'm a physicist, a lot of them are wrong in the sense that they are not like ray traced diagrams. They're more trying to convey an idea. So a lot of times in like optical textbooks, dealing with the human eye and all this kind of stuff, they cheat a little bit with the rays that they're doing, right? So realize that these might not exactly line up with like the simulation I showed you and some of the drawings we were doing about like converging and diverging lenses. We're trying to kind of give you an idea of the differences that are taking place, right? So for distant objects, and when a physicist or an optician says a distant object, we're talking about something that's so far away that it might as well be infinitely far away. And infinity in optics means the light is coming into the lens. All the rays are essentially moving parallel to the optical axis. In practical terms, basically 5 meters in front of a human eyeball, roughly 15 feet, okay, in front of our faces, everything 15 feet and further away might as well be infinitely far away, okay, as far as the lenses in our eyes are concerned. Things more than 15 feet away, all of the light rays are coming more or less parallel to the optical axis, and so therefore all of those rays will come together and focus at the focal point of the lens, which is where I start getting a little bit of an issue with some of these drawings, because you see how they draw it so that the rays come in and then they kind of bend down and focus at a point, okay? The focal point of the lens, of the cornea and lens in our eyes, is not our retina. We're trying to put images in focus on our retina, but if the focal point was our retina, what would we see? If the focal point of the lens in our eye was at the place where we gather all the information, what would we see? Remember, what's the focal point of any lens? It's where all the light comes together, right? Okay. What would we see if the lens's focal point were right on our retina? We would just see a bright dot. Okay? We wouldn't see images form at all, right? So the issue I tend to have with a lot of these diagrams is not showing us where the focal points are, right? They're not doing the correct rays. But it's okay, because like in this case, we can kind of see the difference between a really distant object where the lens is relaxed versus a close-up object where the lens is tensed. You can kind of see how the image got bigger on the retina because of the difference in object distance. But if you do another, at the risk of giving you an ocular headache, okay? Remember that thing we were doing where we were switching back and forth from distant to up close? Now what I want you to do is I want you to look at your fingers and then just bring them towards your face and keep them in focus as long as you can. Okay? Like you'll even kind of go cross-eyed a little bit, right? Concentrate on what it feels like in your eye to have something really up close and be trying to focus on it. What does it feel like to try to focus on something really close to you? It hurts, doesn't it? Okay? There's strain. That's because for objects that are closer to our eyeballs, our lens, the muscles, the ciliary muscles in our eyes have to pull. Am I right? Muscles only pull. Is that correct? Any kinesiology majors out there? Right? Yeah. Muscles can never push. They can only pull. And so you need like a tricep and a bicep to be able to do this motion as well as like this motion. Anyway. So what?
The gym was a lie?
Oh yeah. Oh yeah. The terminology that they use in different areas is totally wrong, right? Okay. But like I'm pretty sure muscles can only like contract and relax. Like they can't like stiffen up and push. So mechanically you have to like have a muscle that's pulling in order for this to be pushing out, right? Plus you have to have bones to make it all work. I'm not a doctor. I just play one in classroom. All right. So where was I going with this? That tensing that you felt as you looked up close at your fingers, okay? Those are the muscles in your eyes straining to change the shape of the lens to try to keep the image in focus on your retina. There are a lot of issues with technology in society today, and I don't want to sound too much like your dad and all that kind of stuff, but I do want to point out a problem that all of us have when it comes to using our devices, right? Whether it is our iPads, our laptops, or our phones, where do we hold these things? Pretty close to our faces, right? Okay? People don't, unless it's your grandparents, they don't walk around, right, doing something like that, right? So we hold them fairly close to our faces. In the case of a cell phone especially, okay, we generally don't tend to hold them up here, right? We tend to hold them right here. And what just happened to all the posture? I'm exaggerating, of course, right? But you've seen people, right? As maybe even yourself, if you hold your phone, you'll start to raise your shoulders, right? You'll bend your neck. And anybody that's studied anatomy and physiology knows that raised shoulders, bent neck, this is a strain position, right? Okay? The relaxed position is shoulders back and down, right? Head straight up, okay? But now my arm's going to get tired, right? I know, let's get one of those hats. And we'll just put an arm on it and I can hold my phone. And I would look like a real dad. A real dad. Anyway, right? So there's better ways to use it, but we do use them right up close to our faces, right? Well, having them close to our faces means that our eyes will be in a constant strain situation. In fact, to fully relax one's eye muscles, where do you have to look? Far away. And how far is far away? 15 feet or more, right? Okay, 5 meters. So in order to fully relax one's eye muscles, you have to look at something that's more than 15 feet away. How hard is it to remember that when you're watching that really good show on your phone? Right? You can watch like a whole movie. Right? And that's 2 hours of eye just completely in its strained situation. What happens when you tense a muscle and you don't give it any relief? It gets tired. It can cramp. Okay? A lot of students will come in and sitting down and grasp, and they're doing this, and they're doing this, and then I'll watch it. I'll watch it happen, right? Their body is telling them that their eyes need a break. Your brain needs a break after 2 minutes, but the eyes, right? The eyes need a break. And I'll watch. They'll sit up, kind of lean back. Notice where they're looking now. Far away, right? They'll rub their eyes. oh, physics is so bad. I can't believe Mr. Balogh is making me do this, which is a false statement. You're making yourself do it. You paid for it, right? But like, you can just see the subconscious mind, right, telling the body something has to change, right? In posture, in vision, all that kind of stuff. Do yourself a favor, try to develop a habit where every 20 minutes, if you've been typing on the computer, working on the iPad, looking at your phone, every 20 minutes, it only takes 30 seconds. That's all it takes, okay? For every 20 minutes, for 30 seconds, look up. Look out the window. Even better, every 20 minutes, stand up from where you are, stretch, walk around, go to the bathroom, get a drink of water, right? Come back, and then focus for another 20 minutes. Like literally focus with your eyes for another 20 minutes, right? Okay? Every 20 minutes, if you give your eyes that 30 seconds of rest by looking out of a window, right? Your eyes won't be in that constant strain. Some of those strain, stress, headaches that maybe you have after long study sessions won't be there. There'll be other mental and emotional traumas from the study, but the actual strain in your eyeballs will be less, right? And these are ways that you can protect your vision, because a strained muscle that stays strained all the time eventually is just going to give up. And you're going to end up not being able to see far away because it's so tight. Okay? All right. So let's talk about what can go wrong, right? And again, the false information conveyed by this diagram never ceases to amaze me. The rays are not focusing on your retina. They can't. They would just see a bright light, right? But they're trying to impress upon your mind that if the eye, for whatever reason, okay, like normal's at the top, the middle one here is for a nearsighted person. It's called myopia, is the medical terminology for it, okay? What's happening is myopic eyes are overachieving. They are focusing too much. And again, this typically isn't caused by the lens, it's caused by the cornea. And the extra powerful focus of a myopic eye is bringing the image away from where the retina is, and so blurriness results. You're going to be able to see this in lab on Monday. You're going to actually have an optical bench and lenses, and you're going to have a screen, and you're going to move that screen back and forth to try to get an image in focus. Focus really is find the place where the light rays are converging, because any other place the light is getting there at different times in different places and the image isn't clear. That's what's going on inside of our eyeballs. If the image isn't forming on our retina and it's forming in front of the retina, then the actual light rays that eventually hit our retina are not all coming together. They're a little bit spread out. For a farsighted eye, hyperopia, the reverse is true. In this eye, the focusing power isn't strong enough. And so the image is actually forming behind the retina. And it's kind of easy to see on this diagram. Like the rays aren't coming together at the same place at the same time. Okay? They're actually kind of spread out, which gives rise to something being out of focus, right? To have something in focus means that you've got the position where the image is forming and the screen, okay, or the retina or whatever, coincident with the focal point of the lens. So, all right, let's do a calculation really quick, because we can actually use our lens maker's equation, and we're going to use this equation for not just the unaided human eyeball, but we're going to use it for when we do corrective optics like eyeglasses and contact lenses and things like that. It's actually the equation that all the computers in the optometrist office use. It works really, really well. So again, that equation, right? Plus 1 over distance to the object, right? There's our lens maker's equation. The lens of your eye is a converging lens. the cornea of your eye is a converging lens, okay? We aren't going to do the case where we treat this as a compound optical system. In other words, we are going to model your entire eyeball as like one optical element, the cornea and lens together, right? And instead of trying to differentiate between them. So that's a little bit of a cheat we're going to make, but it's the same one that the ophthalmologists do, and so, sorry, the optometrists do. An optometrist is a doctor that's responsible for correcting your vision if you have vision problems. An ophthalmologist, did I pronounce that right? Is an eye doctor who's concerned with the actual health of your eye, right? And is also sometimes an eye surgeon, right? So whenever you go to get an eye exam, do make sure that there are two doctors there, right? There'll be an optometrist who's helping correct your vision or detect if there's a vision problem with like your perception of light. But then an ophthalmologist will actually go and check the health of your eyeball to make sure there isn't too much pressure in the eyeball, that your retina is healthy, that the movement of the muscles of your eye are correct, all that kind of stuff. So this all, of course, depends on insurance and stuff, but if you have the coverage and make sure that you're going to a place that does, because a lot of places, like in Walmart or something, where they'll have an optometrist in the optical department, but they won't have an ophthalmologist, right? Somebody that's concerned with the health of your eye. It's important to have both checked every year. Okay, so let's, what we're going to do is we're going to calculate for the nearsighted eye and the far, actually that's not what we're going to do, I lied. What we're going to do is we are going to calculate the image distance for so for an unaided normal eyeball when we look at something far away, okay? What's the image distance? And then what happens when we look at objects that are up close? Again, what's the image distance? What we're going to do is we're going to compare and contrast the location of those two image distances, like how far apart do those images form for the far away image versus the up close image. And we're going to see just how tight the tolerances are on the human eyeball for keeping things in focus. So let's do the object distance is effectively infinity, right? So as long as the object is 15 feet or more away from a standard human eyeball, right? What would the focal length, yeah, I want to calculate focal length. Look at your notes, Mr. Balogh. Make sure you're doing this right. Did that. Yeah, we're going to calculate the focal points for these. And we are going to use, for the image distance, we're going to use the average distance from the front of the cornea to the back of the eye for an adult human, okay? That's 2.5 centimeters, okay? So basically, we have to form, right? This is the front of the eye, and then we need to form an image, right? 2.5 centimeters away, okay? In all cases. So what we're going to do is we're going to find the focal length of the lens necessary to pull this off, right? Well, for the infinitely far away object, what's 1 over infinity? Which one do you want to pick, Sue? Okay, get small, right? Matter of fact, it's so small it's 0, right? 1 over a really big number is trending towards 0. In physics, we don't care about the limit, is whatever goes to 0. We just say it's 0, right? Mathematicians will complain about it's undefined algebraic, blah, blah, blah. No, it's 0, okay? So that goes to 0. And then this focal length is pretty easy to calculate, right? Okay, it's just going to be 2.5 centimeters. So the focal length of the optical system in your eye needs to be 2.5 centimeters in order for you to see something far away. Okay, we're going to do the up close, okay? The distance to the object, up close. The what we call the normal near point, okay? A near point in optics, in optical medicine, is the point, the closest point to your eye where you can keep things in focus, in relative comfort, okay? So for the average adult eyeball, that near point is 25 centimeters. Symbol is near point, right? 25 centimeters for the normal adult human eyeball. And when I say normal, I mean like unaided, it's not nearsighted, it's not farsighted. It can do all of the distances and keep things in focus. It of course varies from person to person, and it changes with age, okay? The near point of a child is like right in their face. If you watch children, they'll pick up something, and if they want to see it in any detail, they'll like bring it right up to their faces, right? If you hand a child a crayon and a coloring book and you tell them the lie that they have to keep the colors inside the lines, right? What do? Right? They'll get right up to it. They'll like have that crayon in their eyeball, right? And they'll get really close, right? That's because their eyes, being all squishy and stuff, they can accommodate really well. They can focus on stuff that's way up close to their eyeballs, and they can focus on stuff that's far away, right? And so they'll be right in there, okay? Compare and contrast that with the, how do I say this nicely? With the people in your life that perhaps have more life experience than you. Am I allowed to use the O word? They're old, right? So what do old people do? Hey, Grandma, look at my phone. What do? Right? Like, why do they have to like hold it so far away? Their near points, okay, their eyes have gotten stiffened up or changed shape or whatever, that the near point is no longer 25 centimeters. Like some people's near points are like 1 meter, 2 meters away from their face. Well, what's the problem when you put something, okay, I can finally, it's in focus now, right? What's the problem with all the writing that might be on it? Now it's too small, right? And so you got to go get the large print edition, right? Or the large print iPad. Have you ever grabbed your grandmother's phone and you're like, I can see like 2 characters per line, right? Okay. They've needed to make it big because it had to be far away, right? To be in focus, but now it's far away and the writing's too small, so they have to make the writing bigger, right? All that kind of stuff. Or they have to put on reading glasses, right? And then you can have like the, I do have reading glasses. I don't use them very much. Where did I put, let's pretend these are my reading glasses. There they go. So these are my old glasses. Boy, I was really blind. Okay, right? But if these were a pair of reading glasses, right, have those people that are maybe more wise than you, right? They look very disapprovingly. Why are they like? Their nose is too small. No. What's going on? The reading glasses help them do what? Read something up close to their eyes, right? Okay. But reading glasses can really only focus like here. But now they have to look at something far away. And if they've cut the glasses up here, it's like I can see here, but right, everything. But if they, I can look over the glasses. I can look at disapprovingly at you, right? But I can also see, like, I can read up close, right? And then see far away, and then read up close. Or they do that annoying thing where they're like that. What did I do with my glasses? Right? Okay. So that's evidence of cognitive decline. So, which I am a party of now that I am over 50. So, if the object distance is up close, the normal near point of 25, okay, what is the focal length of the lens going to be now? Well, again, the image distance is still 2.5, okay, and I'm working all in centimeters, right? So now it's going to be 1 over 25. Those are both in centimeters, so we're in good shape. And when I did that calculation, I got 2.3 centimeters. So what's the difference in focal length needed for an object at infinity versus an object up close? It's 2 millimeters, right? 0.2 centimeters, which is 2 millimeters. That means that if the eye loses the ability to focus, right, and can no longer focus within that 2 millimeter range, or, which is more likely, the shape of the eyeball changes sufficiently so that a bigger than 2 millimeter change in the length of the eyeball happens, what happens to vision? It gets blurry. It's a finely tuned instrument, right, that when there are either accommodation or refractive power changes, meaning the cornea and the lens, or the shape of the eye changes along its optical axis, the length, the front to the back length, you will end up with vision problems, right? Which is no surprise why so many people have to have some amount of corrective help to fix their vision problems. And we're going to get into all those here in a second, but I just want to kind of help you appreciate sort of how finely tuned this is. Most human eyes are not perfectly spherical or round, okay? In fact, the normal shape of the eye is more of like a kind of a, like a football or an almondy shape, okay? And I'm talking like front to back. I'm not talking like the shape of our eyes in front, okay? Different racial features will like rotate the eyes or make them appear longer, one dimension or whatever, right? What's kind of universal though is that in infants, kids, puppies, kitties, whatever, right? Okay, any young form, right, of a biological entity, their eyes will be really big compared to the rest of their face. Eyes actually don't change their size very much from birth to death, okay? They're actually kind of an organ that stays the same relative size. And as a child grows and the bones in their skull get bigger, right, the eyes will sort of take up less and less of the amount of face, right? But it's one of the things that we humans pick up on. Oh, it's so cute, right? Why is it so cute? Big old alien eyes, right? Like next time you watch a Disney film and they want to anthropomorphize like the frog, right? In The Princess and the Frog, right? Okay, like notice what they're doing in the cartoon, right? They're exaggerating the size of the eyeballs, and what is making the eyeballs look big do? Makes it look cute, just like kids, right? So that's kind of what's going on there. As we age, our lenses stiffen up, our eyes kind of lock into a position. They can get really long. In the case of my eyes, for whatever reason, my cornea lens just started overachieving, and right around age 12, 13, I noticed I would be in class and I'd be sitting right there and I could not read what was on the board. Like I didn't understand what was going on, but I was just like, can you write that bigger? And the teacher's finally like, you need to go get checked out, right? And I did. I went down and I found out, right, that was really close to being legally blind, okay? Let's start talking about like optical defects here, okay? So this right here is what a far-sighted person experiences. When we say far-sighted, in medical optics, it's referring to the patient's ability to focus. Farsightedness means that they can see far away without any help. But what happens to all the stuff that's up close? It goes away. So a farsighted person, what's their problem? They can't see things close up. Do you see how it always felt a little bit backwards in my mind, right? But it's the way it is, right? But a far-sighted person can see far away, meaning the problem is with things that are up close, okay? Things that are up close are out of focus, okay? So what do we do to help fix that, okay? And this is quite possibly the hardest thing to learn about corrective optics. We're talking about putting glasses in front of a person's face, in front of their eyes, to be able to correct their vision. In corrective optics, we are not changing their natural near and far point. What do I mean by that? A far-sighted person has a near point that has a problem. What's the standard near point for the human eyeball? 25 centimeters, right? Basically the distance somebody would hold a book or a phone or something from their face, okay? From their eye. A far-sighted person can't focus that close to their face. And so their near point, the point at which they can see something in focus, has been pushed out away from their face. So a far-sighted person has a near point that is greater than 25 centimeters. Like, again, on average, the 25 centimeters is for adult human. So if you go into the doctor and you get measured and you find that your near point is 1 meter, right? That means that your eye can focus on things that are 1 meter away from it, but no closer. So the goal for any corrective optic, glasses, contact lenses, LASIK, whatever, okay? Actually not LASIK, because we're actually changing a lot more there. But for glasses or contact lenses, the goal is to put the image formed by the glasses at the point where the person can actually see it. Okay? So glasses don't change the near point for a far-sighted person. What do they do? They create an image where that person can see it. So if we do an example, did I write down an example here? Farsighted, yes. Okay, so let's say that the near point for a farsighted individual, okay, is measured to be 57 centimeters. So a little bit more than half a meter from their face and closer, they can't focus on anything. That near point for that individual is where they can see stuff. And so we're going to set the image that is formed by the glasses or contact lenses we're going to give them. We want to put the image at that near point. So the image distance is going to be 57 centimeters. Where do we want a farsighted person to be able to hold the thing they're reading? At 25, at the normal near point, right, for an eye that doesn't have any trouble, right? So the object distance where we're going to put the object is 25 centimeters. But we're going to form the image at the patient's near point, right, which isn't 25 centimeters. Okay? So we set it to be 25 centimeters. Notice in these pictures right here, right? The object, we're not changing the object's position, right? What we're doing is we're forming an image of that object at the place where the person can see it. The person can see it at 57. That's where we're going to make the image. Okay? So we go and calculate the focal length of the lens that is necessary for for this to take place, okay? So we go 1 over distance to the object, 25 centimeters, plus 1 over distance to the image, 57 centimeters. Okay, we need to talk about signs really quick. What do the sign conventions have to say about image distance and object distance? What side of the lens is the front side? It's where the object is. So where's the front side of your eyeball, optically speaking? Everything out, right? It's not in. It's everything out here, because all the objects are out here, aren't they? So the front side, right, is here. The back side, I mean, you can draw the line at the eyeball. You can draw it at where the lens is. Some problems might try to oh, well, the glasses sit 1.5 centimeters in front of their lens of their eye. They're just being stupid, right? I wouldn't do that to you on an exam. If you get something like that in homework or an example or ChatGPT throws it at you, just realize you have to kind of correct. Like if they say the glasses are 1.5 centimeters away from the lens of your eye, you kind of have to correct the image distances, whatever it is, minus the 1.5. Anyway, because they'll reference from the front of the eye, and then it's not necessary because we actually don't do that. Anyway, in practice, in the doctor's office. They do something else that I'll talk about later. Okay, so when the object is on the front side of the lens, the object distance is what? Positive or negative? Positive. Where's this image forming? Is the image on the front or back side of this lens? This shouldn't be a hard question, but your brain just seized up a little bit, I can tell, because everybody gets tripped up on this, right? Because you want to say, well, duh, the image is forming on the retina. We just put a corrective lens in here. We're talking about what is this lens doing. This lens has an object, and where is the image forming? On the front side of the lens. No matter how many times I say it, people, again, this is one of those things about the human mind, some reason it just can't wrap its brain around it, okay? You got the idea of what I just said. Where are we trying to form an image? For a person that needs their vision corrected, where are we trying to put an image? Where they can see it. This has nothing to do with what's going on the retina. It has everything to do with what's going on the front of their faces, right? If a person can see things up close at 57 centimeters but no closer, the image we want to form from the glasses we put in front of their face has to be at 57 centimeters. We want to put an image where they can focus on it, okay? So that image distance has to be negative. Didn't leave any room. Negative 57 centimeters. Why does it have to be negative? Look at the sign conventions. When the image forms on the front side of a lens, the same side that the object is on, what's its sign? It's a negative sign. All right. So we got that all sorted out. And the focal lengths that you get for this one, I calculated it somewhere. 44 centimeters. That's the focal length of the lens that needs to be in the glasses or the contact lens. Don't ever do farsightedness with a contact lens. That's stupid. Okay? But this would be the focal length of the reading glasses that this person would need in order to be able to see anything at 25 centimeters in front of their face. However, glasses, especially reading glasses, which you can go down like to the dollar store or Amazon or the pharmacy, you can just buy them right off the rack. You don't need a prescription for reading glasses. They don't sell them according to focal length. Instead, they'll sell them according to refractive power. And that refractive power is the inverse of the focal length. So in optometry, rather than solving for the focal length, they just kind of keep it as 1 over f, right? So they don't have to do that final inversion, right? And so if you don't do the final 1 over x, this turns out to be 2.27 diopters. A diopter, capital D, is an inverse meter. Okay? And so if you need reading glasses or you've ever helped anybody purchase reading glasses, they might go down to the store and you'll have a reading glass that says +2. That's a 2 diopter refractive power. Okay? It's got a focal length of 0.5 meter. How'd I do that? What's the focal length if you know the diopters? You just invert it. Okay? So +2, what's the plus mean? What does the sign conventions tell you? What kind of lens is it? If the focal length is positive, it's a converging lens. That's what reading glasses are. They're magnifying glasses, okay? It's just a question of how much do they need to magnify, right? It's also not super critical to get exactly the person's near point, okay? So even though this patient needs a 2.27 diopter lens, we'll probably give them like a 2 1/4 diopter set of reading glasses. The human eyeball is pretty capable of doing some accommodation of its own. They could even read like with a positive 2.5 or even a positive 3. They could go down to positive 1.5. In optometry, there is a bit of the human factor and some artistry that goes into helping the patient be comfortable with the change that's going on to their eyesight. You can sit down and the computers can be hyper accurate. If you've ever been and gone and gotten an eye exam, they have you stare into the machines and they'll show like a balloon on a road or a boat on the sea or whatever, right? Okay. That's just giving your eyes something to do while the lasers, the infrared lasers, like map your eyeball and they just tell the doctor exactly what the correction has to be, right? For all these different things to happen. The problem is that if the doctor goes in and sits down and puts that exact correction on that big thing that they put in front of your eyes, right, your face to be able to do stuff, you won't like it. You'll say it's either too strong or too weak or it's not in focus or something like that. Then they go through a game. Anybody who's been to an eye exam knows the game, right? Okay, look at the thing on the far side of the wall. All right, is it 1 or 2? They'll do a click, right? 3, click. 4, right? What are they doing? When they do that little click with the thing that you're looking through, what are they doing? They're changing the focal length of the lens. Or in some cases, we'll get into astigmatism later, they're changing the focal axis of the lens, okay? So what they're doing is they're asking you as the patient, what is your perception of this? Because there's more going on than the strict optics of the eyeball. There's how your brain is interpreting the optical signals, right? And some people will say, oh, okay, now it looks bolder, or now it looks more fuzzy, or there's less contrast, right? And they're trying to find what's comfortable for the patient as opposed to what's actually like the physics, right, of the eyeball that is necessary. So it's a bit in between. And optometrists are trained to be able to help you figure out, right, what the best combination of correction is. We will, in this class, only consider the pure physics of the eyeball, right? We won't take patient preference into account. Okay, so this is an example of what nearsightedness looks like, okay? A nearsighted person can see what? it can see close, right? Right? Nearsighted means they can see up close. In fact, a lot of nearsighted people have pretty small near points, but that's not the important part that we need to focus on. Haha, pun intended. For a nearsighted person. A nearsighted person's far point is not infinity. So for a normal, healthy eyeball, a near point of 25, meaning they can focus on things up to 25 centimeters in front of their face, and the normal far point is infinity, meaning that you can focus on things no matter how far away from your face they are. A nearsighted person's far point is no longer infinity. Okay? We say that their far point has been depressed, right? It's been brought in. Peak blindness for me, right? When I was wearing my thick Coke bottle glasses, right? My far point for my left eye was right there. Right? Meaning that through my left eye, I could see no further than this. Right? Everything in front of there was totally in focus. In fact, if I was like soldering or sewing or doing something really fine detail, right? I would just take my glasses off and like a kid, I would just hold it right up to my left eye, right? Because I could see really well that fine detail, okay? My right eye was about like this, okay? And so like basically anything past here was totally out of focus for me, okay? At the worst correction that I needed. Most far points are, 1 meter, 2 meters, 3 meters away. Basically, any far point that is less than 5 meters, right, infinitely far away, there's some sort of vision problem happening, right? Some inability to focus on things that are far away, be it a street sign, stop sign, whatever, okay? Can't see it. The glasses help, okay, to bring those distant objects into focus. And again, with corrective optics, what are we trying to do? Where do we put the images that are formed by the lenses in their glasses? Where they can see it. So for me, that had a far point measured in like 10 centimeters, okay? What my glasses were doing was creating an image of distant objects at my far point, the place where I could see it. Now, since nearsighted eyeballs are overachieving and focusing too much, it should come as no surprise that the kind of lens that a nearsighted person needs is a diverging lens. We need to help spread out some of the light so that when the eyeball overfocuses, it won't be much of a problem, okay? So, we are going to be forming, right, the image at the person's far point. Remember, a nearsighted person has a problem with their far point, okay? A normal far point is infinity, right? But for a nearsighted person, that far point is going to be something else, okay? So let's just say that we measure a far point of 45 centimeters. Again, this means that the patient cannot see past 45 centimeters in front of their face. Everything beyond 45 centimeters is out of focus. When we say distant object, what we're saying is infinitely far away. Okay? And what's infinity for the human eyeball? 15 feet. Right? Okay, basically anything past 15 feet is infinitely far away. Okay, so now we're going to solve for the focal length of lens that's necessary to pull this off. Okay? So the far point becomes the image distance, but critically we have to think about the sign conventions. Okay? So let's erase that, right? Let's just write, what does the image distance have to be? Positive or negative? What side of the lens, front or back, is this image forming on? What side of the lens is the front side? Side with the object. Where is the image forming? On the object side or on like the retina side? It's on the object side. So what is the image distance going to be? It has to be negative again, right? And the image is going to form at that person's far point. Okay, so we've got our 45 centimeters. So 1 over distance to the object, infinity, plus 1 over a negative 45. Drop dead easy math for the nearsighted eyeball. Anybody with myopia, if you know their far point, you know the focal length of lens that they need. Because 1 over infinity is 0, and then all you're left with is whatever the distance to the far point was. Okay? So there's the focal length of lens. The power would be negative 2.2 diopters. Okay? And what's the negative sign mean? It's a diverging lens. So people that are nearsighted have diverging lenses in their glasses or their contact lenses. People who are farsighted have converging lenses in their reading glasses. In both cases, what kind of images are they looking at? Are they real or virtual? They were both virtual. A diverging lens can never create a real image. A converging lens can, but we are producing an image on the same side as the object for the lens, which means it has to be virtual. So if you're wearing contact lenses right now, if you're wearing glasses right now, guess what? You're experiencing virtual reality. No, I mean, real rays will get to your retina and images will form and all that kind of stuff in your brain. And you are not handicapped in any sense of the word in terms of like driving ability or ability to perceive. As long as your glasses are on, right? Your depth perception will be correct, all that kind of stuff, right? It's just that the images you are seeing through your glasses, through your contact lenses, are virtual images, placed at the position where your natural biology is able to focus on it. So for a myopic individual, taking things that are far away, that are out of focus, and making sure that those images form at the place where you can focus on them. All the other depth perception, everything is handled by your brain, and there's no like weirdness going on there. It's not like you have to like retrain your brain to make it work. Now, people who are new to glasses or people who have had glasses and get a new prescription sometimes will have a bit of a headache, slight motion sickness as you get used to the new prescription. Okay, that is very common. What's going on there is your brain is trying to make sense of the new positions of things, but it can usually do it fairly quickly. If you continue to have problems with your new glasses, you need to go and have the new glasses checked for accuracy. Okay. And a lot of glass manufacturers at the glass store, they have like warranties, right? For 30 days, for 90 days, right? You can bring your glasses in and they will check them to make sure that the lab that ground the lens actually did it correctly, right? And it's actually pretty easy to check what's going on with lenses. Okay, so we've done the nearsighted and farsighted eye. Let's do a quiz. Because I have way too much fun with optics, I'm not going to finish chapter 20. You have all of the information you need to do the homework, but let's just do a couple of other things because people always ask. Astigmatism, okay? If you have astigmatism, this means that the horizontal and vertical focal lengths of the lens in your eye are different. Normally, in a symmetric lens, there is no difference of focal length horizontally and vertically, but in true lenses, like in the human body, they can be different. You could have different focal power vertically in your eye than horizontally, and what's more, the axis of that focus can actually be rotated, okay? 21 of, well, basically 90 degrees, which covers all 360 of them. Anyway, In astigmatism, you need to pull those different focal lengths along different axes into the same place so that the image can form. In an eyeglass prescription, you will see various codes. They'll say like cylindrical, and they'll give some numbers, and then they'll give axis and some numbers, and all these different kinds of things. The cylindrical correction is for astigmatism. If you see any number in the cylindrical column of your prescription, that means you have some kind of astigmatism. Now, normally, people have very slight astigmatism and don't realize it. Literally, you can blink like 4 times and your brain will overcome a slight astigmatism. Okay? It's the stronger astigmatisms that need correction. I have a slight astigmatism, or I did before I got my LASIK. And I was trying contact lenses at one point, which never really worked for me. But astigmatism glasses and contact lenses, you need to like nail the axis along which the astigmatism is happening. If you have an astigmatism, you have glasses right now, you can take them off and rotate your glasses and the whole world will shift its focus, okay? But for the contact lenses, I'd have to put them in and I have to blink several times. For the contact, it was weighted. It would rotate and it would rotate into its correct orientation. And while it was rotating, the whole universe was going out of it. Who needs drugs when you have physics, right? Like, I mean, it was crazy. Our perception of how big or small objects are has everything to do with how much of their field of view, how much they take up our field of view. Field of view is like what we can see. Roughly for us, it's about 180 degrees, okay? If you hold your hands off to your side and you kind of wiggle your fingers, you can tell that something's going on out there, okay? Some people have a little bit more limited, right? It really doesn't go past the edges of our face. But if an object is taking up a big portion of that field of view, we tend to think of it as either being magnified or really close to us, depending. If it takes up a little tiny portion of our field of view, we say that it's smaller, or our brain says it's smaller, and we tend to interpret that as far away. And the reason I'm talking about this is because magnifying glasses, telescopes, and microscopes are all based on this idea of taking something that's either far away and really small or something that's up close and really small and making it look bigger, right? And so a magnifying glass will take the object, put it way inside the focal length. The image that is formed is virtual, it's magnified, and it's upright. But because our perception of that virtual image is that it takes up a lot of our field of view, and so we'll say that it's bigger. It's been magnified. It's not the correct size based on our interpretation, right? We know that the lettering on this map, right, isn't that big. But as we look at the virtual image, we perceive it as being magnified or bigger than it should be. And the reason we see that is because the magnification has caused it to take up more of our field of view. Okay? Same thing goes for a microscope. Okay? In the microscope, again, we're taking something that's really, really tiny, and when we look through the microscope, that little tiny thing takes up a lot of our field of view. And so we perceive it as being magnified. In the case of a telescope, okay, we're taking something that's very far away and tiny and trying to pull off the same thing. But we're doing it with multiple optical systems, okay? One of the things, and I'll just leave you with this so you have the equations with which to calculate it. For a magnifying glass, the magnification is the near point divided by the focal length of the lens. And again, the near point is 25 centimeters, okay? So whatever the focal length of your lens, 25 divided by the focal length, the magnification of the magnifying glass will be given. So if the magnification's 3, right? Well, let's do 5. If the magnification's 5, then I can tell you right now the focal length of that is 5 centimeters, right? Because I can divide. When it comes to microscopes, this gets a little bit more dicey okay? The magnification for a microscope is negative L, which is roughly the distance between the objective lens and the eyepiece, divided by the focal length of the objective lens, 25 over the focal length of the eyepiece. FO here, this is the objective lens, and that's the eyepiece, right? There's two optics in a microscope, okay? The L there, the L isn't exactly the distance between the lenses. It sort of is. It's usually something you either have to be told or you have to measure. For a telescope, it's a lot easier. It's the focal length of the objective divided by the focal length of the eyepiece, okay? The length of a telescope will always be the sum of those focal lengths. And that just comes down to the fact that telescopes are looking at things far away, and so the object distance is infinity, which makes it much easier to do the calculations. But for a microscope, things are up close, objects aren't infinitely far away. It gets a little bit dicier to do it, which is why the microscope's equations are just a little bit more complicated. Otherwise, you're usually told all the information, and you go ahead and you plug and you chug. I think, I don't really have to talk about any of that. So yeah, no, actually, I did it. I finished chapter 26, okay? So I'll see you on Monday for our optics lab, where we'll actually build telescopes, microscopes, and do some stuff with lenses. And then we'll move into chapter 27 starting next Tuesday. There's a 95% chance I will not be here tomorrow, okay? So you may not want to come looking for me. Grass will more than likely open at 8 instead of 7. So just so you know. I'll put out an announcement telling you definitely what's going on.